Giving me this opportunity to come over to this university and to be there in this inaugural day program. Before I start, I should congratulate everyone here at Dehradun for the 25th Formation Day celebration. Congratulations for the state. And also to the university, the Graphics Era University, for organizing this conference in its campus under the auspices of its Department of Aerospace Engineering and Mechanical Engineering. So congratulations once again. I'm sure it will inspire young people here. In fact, before I started talking about it, whatever I wanted to speak has already been told by Dr. Saraswat as well as Mr. Athana Mukherjee, highlighting the issues of combustion, the sustainability and net zero goals that we have set for ourselves. I, being a rocket man, rocket propulsion person, I thought that I will talk about the domains which is more explicitly, though you are not looking at the higher levels of problem, but the more intricate problems which are there for combusting people. I think that should be the one which is important for you to write papers and do research in this domain. I think it's going to be very important for each one of you. But of course, they are all connected. The major issues that were highlighted are of the issues of the fuel, the issues of the combustion, the issues of the efficiency, all become very, very important. But before I start, I think all of you know burning of anything really releases thermal energy. Before human beings started looking at it, things were burning all the time in the world. Wood burns, fuel burns. But burning is a process which is a slow rate of release of energy due to the reaction of the fuel with the oxidizer or maybe the oxygen. But combustion is not just not burning, it is a controlled release of energy at a higher rate. Then we call it is combustion. That if you progress it further, you may lead it up to detonation, which is a very high rate of release of energy. Possibly it's not really a reaction of the combustion, it is a different process. So we in rocket people, we deal with all this, the burning to combustion to detonation. I think it's a process of transition of various reaction levels. But then this burning could happen or a combustion could happen because of the reaction with oxygen, but then it could also be a decomposition process where thermal energy is released. So we have different ways of achieving this type of combustion in a controlled manner. But the interesting part of this combustion is that the combustion allows us to release a chemical energy which is resident in materials into thermal energy. But thermal energy per se doesn't do anything unless you transform that thermal energy into mechanical energy, and the mechanical energy into some useful result, possibly in the form of electrical energy or a useful work which you are looking at. And the whole chain transitioning from the chemical energy to the useful outcome, which is the point where we are all interested. In that, combustion becomes one important element in the cycle efficiency of this transition from one form of energy to another. And your interventions in terms of research will help in each of this, as mentioned about the materials onwards. I think many of them will play a great role. The human beings in its evolution, mobility became an important topic, the how to travel faster. I think there is this role of this chemical energy resident in materials. They are extracted to generate mechanical energy to add to the mobility. That's why we have aircrafts, we have cars, we have automotives, we have rockets, that allows us to travel faster from one place to another. I think we have realized only this energy, that the chemical energy resident in materials, to be released to do this type of work. I think this is a fantastic discovery of the human race to allowing us to progress to society. I think this is something which you should all be aware of. But then the propulsion which we use in rockets, it's a different form of energy release. The differentiation between a combustion happening in an IC engine or an engine which we call gas turbine to a rocket engine is entirely different. Though the principles may be the same, here the rate of energy release and the quantum of fuel which is consumed is of much, maybe an order, maybe few orders in magnitude. So the energy density which is resident in a given volume in a rocket engine is of much, much higher. For example, if you look at an aircraft engine, typically an aircraft engine will produce a 20-ton thrust. The fuel flow rates are much, much smaller. If you combine a rocket engine, the flow rates are extremely high and the power density available in those devices becomes very high. Typically, an engine which weighs 500 kilogram of an aircraft engine will have a few kilowatt of power, whereas a 500 kilogram mass of a rocket engine will produce few megawatt of power. So this is the type of difference in engine in terms of energy release. So the problems also with the combustion in each of them will differ because of the rate of energy release is very, very high. Of course, why we look at combustion as a scientific problem? I think this is something which is important. Those who are in researchers, we know that we look at always looking at how efficiency can be increased. The question of converting, extracting chemical energy into thermal energy, how we can maximize it, or even converting the thermal energy into mechanical energy, how we can maximize it by appropriate interventions of research into it. And there are many domains. I think you are going to have papers, discussion in each of them. I think this is something which is important for us in rocket. Atomization is one important domain. How fuel is looked at and how you are able to atomize it into certain structure of the particle size. We say that atomizing too much sometimes becomes a problem. Atomizing to a certain level is the right level, because in rocket engines, I am very familiar, the issues of instability of combustion. Combustion is such a phenomena where unless you are able to control the energy release in a stable manner, you will not be able to achieve various performance parameters. For example, instabilities of nature, different nature. You have low frequency instabilities, you have high frequency instabilities, and this can be very well controlled only by the atomization processes, in which the right type of the size is needed, where the energy release is happening at a very controlled manner. The surface area versus the volume is so critical. How do you arrive at it, and how do you achieve it through injection pressures, the pressure drop calculations? It becomes very complicated in terms of rocket engines. I am sure it is equally in terms of the combustors in aircraft engines and IC engines, and of the turbines that we know about. So this is one of the very core research area in terms of increasing efficiency, increasing stability of engines, and all of you know, even rocket engines you need to achieve throttling. They don't operate most of the time in stable, steady state conditions. They need to operate at 100% to something like 40% thrust levels. When rockets come and land, as Elon Musk always does, this engine is very, very capable engine in which you can operate at very high range of operation conditions by controlling the fuel flow rate and atomization. Where if you change its stable operating conditions, it can get into thermal runaway as well as instabilities of high vibration levels, etc. So this becomes a very core research domain in which how do you control atomization in injectors. And injectors in aircraft also have similar issues. Similarly, the issues of heat transfer. I think the fuel, when you flow through the channels of an engine, rocket engine or even aircraft engine, you need to preheat it to conditions of just below the working conditions, and you are atomize it at a highest temperature so that you achieve certain combustion efficiency in terms of energy release. And if all the energy is released immediately, also you have a problem. You will end up with hot spots in the combustors, and you need to gradually release the energy over a distance on which the whole material travel through the combustion chambers. So the engineering of this, how the flow happens inside the combustion processes, and then the rate of release of energy over a distance, whereby which you control the heat transfer release and then save the materials around it. Because the material technology also limits us in terms of the temperatures that are encountered. In rockets, the combustion temperatures normally go above 3000 Kelvin, but the materials are typically handling only over 2500. So how do you really create a combustion chamber which you have very high hot zones, where the materials are capable of only 1000, but you handle gases 3000 Kelvin. So this is achieved by special flow methods by which you create layers of temperature layers, in which the outer layer is always cooler and inner layers are very, very hot, and progressively you bring the temperature down. This is very core of the thermal engineering or combustion engineering problem of combustors. And here a lot of studies are done in computational fluid dynamics and atomization, evaporation of fuel, and how energy release happens in very controlled manner. Even with all of this, our rocket engines are hot spots. You would have seen, when you look at an image of a rocket engine being fired, you will always see hot spots being developing, expanding over surfaces. It's not a uniform temperature any longer. So this is a huge problem of how thermal analysis is done while fuel takes through various passages in engines and of various nature. Yet another issue is, of course, is the material reactivity. This is again a major problem. In many times you will see the materials are sitting inside a chamber where there is a fuel which is a reactive element, the oxidizer. Oxygen is also reactive material. Material get reacted to this, and how do we control this? The coatings, the processes, etc. going into the manufacturing of these engines becomes very important. Its life, reusability becomes an important topic. And how do you control this? By appropriate control of the combustion processes. For fuels of this nature, you will see that, for example, the carbonaceous fuel, of course, will go into soot formation, which is again another major problem in big engine development. When it passes through channels, especially rocket engines, through finer channels, it will travel and get heated up. And if this fuel has higher complex molecules, it can create soot, and over a period of time, it will create blockages and make the rocket engine, again, cause premature failures, or sometimes reusability becomes a problem. So the fuel, the nature of the fuel, the molecular structure of the fuel, and how do you control the temperatures at various points so as to prevent soot formation is a very critical issue, especially in rockets like semi-cryogenic engines where we use kerosene or varieties of kerosene as a fuel. Even in aircraft engines, this problem could be there in some of the combustors. So this is again a major issue. Similarly, for engines which are reusable, all the engines in aircrafts are reusable because after landing, they take off immediately. Very little is attended to these aircraft engines. But the design is such that they are reusable in multiple times without ever attending to it. And you will be surprised to know the core of engineering in the building complex aircraft engines are so enormous. I think there could be experts who can speak better about it. But then rockets are now becoming reusable rockets, and rocket engines are being reused without any maintenance at all. As soon as it lands, a little bit of testing is done and it is ready for next launch, which was not the case in the past. I think this is also a transformation happening because of the engineering detailing that has gone into building this rocket engine, specifically addressing reusability, is very, very important. Of course, this is very crucial. The whole combustion research is crucial from this point. How do you really handle life of hardwares and also its maintenance cost? So unless you pay attention to these aspects, they become extremely, very costly and non-maintainable over long periods of time. But then we have many other challenges, especially with regard to coal and wood. I think you would have noted that today we have issues of energies coming for stationary ground-based engines, and this becomes the source of energy, and their gasification combustion becomes another huge topic. I think a lot of the laboratories that are established looks at some of these combustion processes, especially one in the Institute of Science, Bangalore, which I am familiar with. My professor was the head of that institution some time back. So I know how they pay attention to using low-grade fuels and generate gasification and then run complex machinery using those gases at a very high levels of efficiency. Of course, when you talk about rocket engines, I think I coming from rocket engine side that I must be interested to speak about it. I think we people are very good in putting a lot of fuel in the rocket. Your rockets are only fuel and the rest of the rocket part are very less, 10 to 15, 20% is only rocket, as you see, but inside is 80% is only fuel. Whether it is a liquid engine or a solid engine, you have almost 80% of the mass of the rocket is only fuel. And in such rockets, the fuels are not the typical fuel that you encounter. For example, in a solid rocket, what is the type of fuel used? Anyone can tell? In a solid rocket engine, the fuel is aluminium. Aluminium in fine powder form is the fuel, and it actually burns and produces aluminium oxide. One of the not a good product at all. It's a very dangerous product, alumina that comes out as particles. And we have binders, rubber materials such as the binders, which again complex molecules. We have liquid engines where we use very hyperbolic fuels, very dangerous fuel like unsymmetrical dimethyl hydrogen tetroxide as an oxidizer, and the product of combustion contains a lot of hydrochloric acid. In fact, a typical rocket engine takeoff, the gas that comes out of the rocket engine in solid fuel contains almost 25 tons of hydrochloric acid that is released into the air. And this hyperbolic fuels also generate so much of complex molecules outside, which are very, very dangerous. So there is a move to move away from some of these fuels into more greener fuels, like the semi-cryogenic and cryogenic fuels. So cryogenic is the best in the lot, the hydrogen and the oxygen. Of course, it produces nothing but the steam, and then one of the best in the class of rocket fuels ever that can be found out. So I think there is nothing better than hydrogen and oxygen that can be used in a rocket system. But the difficulty with us, hydrogen and oxygen, is that you have to operate with liquefied hydrogen at 20 Kelvin, and the volumetric efficiency is very poor. We need huge tanks, and to handle it is again a very large infrastructure is required, chilling it and maintaining it and filling it at the right time. You cannot even fill it early, just half an hour. Even just at liftoff, you are still filling the hydrogen because you need to handle the evaporation. So making hydrogen engine and cryogenic engines for long duration space mission is not a possibility, but it's still the best rocket fuel. But then people move away from hydrogen-based propulsion to semi-cryogenic, where you use either methane or the kerosene varieties, where you don't have to keep them at very low temperature. You need to handle only liquid oxygen, which is moderate to handle something like 70, 75 Kelvin, you can handle it. So with liquid oxygen and kerosene, we create the semi-cryogenic engine, which has a very high thrust to its volumetric efficiency, so we can keep it at moderate levels, moderately high levels, and you can handle tanks which are manageable. So generally we go into combustion with these type of fuels now, and all our research that's happening in ISRO and many other places are more into such fuels now, because they are cheaper compared to this and less polluting over long periods of time. So rocket goes into space, and space is also getting polluted because of this, not just our ground. Most of the air traffic, though they are at 10-15 kilometers, but rockets go much beyond it in the altitudes much higher. They give out such polluting gases, and something that we need to worry about over long periods of time. So when you look into these type of combustion problems in these engines, and being familiar with this type of rocket engine development, the whole process of combustion development runs into years. A typical rocket engine development process runs into typically 6 to 10 years of development cycle. And the basic research actually happens from looking at atomization. So the very first study of any rocket engine development is into how to atomize the fuel at the required level, and we start with injectors. And injector characterization of various nature, whether it is a plain injector, coaxial injectors, swirl injectors, and you look at atomization as a fundamental problem in injector development. And injector development and combustion studies progress to a certain level. Then we look at collection of injectors. Typically a rocket engine head will contains hundreds of injectors. A small engine with a 100-ton class of thrust which producing will contain typically 200 to 300 injectors at the head to handle this type of atomization of various concentration and distribution to maintain the temperature profile which I mentioned about. And this whole process will take about typically 3-4 years to finalize, then reach an engine level. Then of course you can look at the turbo machinery, etc., which makes the combustion supporting infrastructure. So the success of an engine development program is actually go around the ability to achieve stable combustion levels with sufficiently high efficiency. We call it an efficiency in rocket engine, not in terms of thermal efficiency, but we use the terminology called specific impulse. Specific impulse is an impulse that is delivered per kilogram flow of fuel. So here again, the combustion engineers and heat transfer engineers have a huge role to play. A lot of research is done in this area. We also have laboratories which looks at the heat transfer problems. We look at the problems of atomization. We look at it in various ways, looking at laser methods to scan it and understand how the atomization processes are happening and how you can control it. We also have mechanisms to look at the instabilities of various nature, look at the dynamics, especially in frequency domain, to see how the combustion process generates various oscillations in it, and how you can control it by geometry, how you can control it by atomization, particle size, distribution, and combustion processes. I think this is a very complex area where huge amount of research is possible. And we have a new fuel now everywhere that people talk about methane. Methane is very interesting because it is similar to oxygen. You compress it, you get a liquid which has a density similar to that of oxygen. Your tank size are well manageable, and you can get a reasonably high efficiency and more of volumetric efficiency as well compared to many other fuels. And it is more greener because of the nature of the molecule. So we are also moving into the methane cycles now. The bigger rocket players are already going into methane rockets, and we are also going slowly into methane rockets. So in this area, combustion research has happened very seriously in our department, and a lot of scientists are working in on methane-based injector development, combustion studies, etc. So let me not prolong. There are huge amount of work that is in and around the combustion processes in engines, in aircraft engines, combustors, as well as in rocket engine combustors. This is a very core area of research in institutions like us and various laboratories which are associated with this. But in terms of the theme that we have set for today, in terms of the net emissions, I believe that as long as combustion is there, this net zero is unattainable. Because we should also realize the basis of the thermodynamics. It doesn't allow you to convert one form of energy to another in real net zero scenario. So it actually limits you from thinking about such concepts. But of course, the role of a combustion scientist is always to look at how we can achieve this energy release at the most efficient manner. In its ability to transform to other forms of energy, like mechanical energy and electrical energy. Ultimately, this only we can do, but then your ability to generate lesser and lesser pollutant through the process is the only thing that you can work around. So I believe that this type of conferences, especially focusing on IC engines, propulsion, combustion, will really help this community to understand the role of the researchers in this particular domain of combustion. Will pave way for making more compact IC engines, because as mentioned here, IC engines will continue to be one of the important mechanical means of converting thermal energy into mechanical energy and other forms of energy, and they are not going to wither away. So is other forms of machines, the turbo machinery class of machines, which will be in a manner to convert the thermal energy into mechanical energy. They will continue to flourish in various forms, especially in the domain of turbines. We see that there is a huge demand for them to come up in the coming days, especially in terms of electrical energy generation. We look for in this country where there is a huge amount of demand to design and develop and install large number of them. So I look forward to this community to work very hard in the research domain, helping us to elevate our knowledge and skill in this domain to help the better design of systems within this country as well. So I want to thank especially the Graphic Era University and also the Combustion Institute of India section headed by Dr. V.K. Saraswat and his team to bring this conference here. Let the engagement with the various institutions in this country grow stronger. In our domain in space, we are very keen to associate with each one of you who have an expertise in this domain to help us scale up our skills and capabilities in this domain in various specific areas which I mentioned. I didn't cover all of them. I think there are many more areas which we should have discussed, but in posterior time I don't go into each of them. So thank you once again. It's a pleasure to come and visit Dehradun and to be amongst you. Thank you, and all the very best to this conference for a fruitful dialogue and engagement, especially with the young people around.
Thank you so very much, sir, for these wonderful words of wisdom. Indeed, a composite capsule full of a lot of information and knowledge. Thank you so very much, sir. It is a privilege to have you here amongst us.